Welcome to Module 2, Locomotion. In this module, we will explore how robots move and the different locomotion methods used in autonomous mobile robotics. Locomotion is the foundation of mobile robotics. Whether a robot moves on wheels, tracks, or legs, understanding how it moves is essential for designing control systems and navigation strategies. In this lecture, we will cover the fundamentals of locomotion, different types of robotic movement, kinematics and dynamic models, control strategies for autonomous movement. By the end, you will have a solid understanding of how robotic locomotion works. Let's begin. Robot locomotion refers to the methods robots use to move from one place to another. It defines how a robot interacts with its environment. There are three main categories of mobile robots. Wheeled robots, the most common due to their efficiency. Legged robots, inspired by nature, capable of handling complex terrain. Tracked robots, used for difficult terrains, such as in military or rescue operations. Among these, wheeled robots are the most widely used because of their stability, efficiency, and ease of control. Understanding these locomotion types helps us develop better navigation and motion planning systems. Asterisk. A robot's movement consists of three core components. Perception, understanding the surroundings using sensors. Navigation, planning both short-term and long-term routes. Control, steering the robot in the desired direction at the desired speed. Each of these plays a crucial role in ensuring that a robot can move autonomously and efficiently in its environment. For example, a warehouse robot must perceive its surroundings, navigate through obstacles, and control its speed and direction to avoid collisions. Asterisk. The type of wheels a robot uses determines how it moves. Wheels are typically categorized into four types. 1. Standard wheels, most common, offering stability but limited movement. 2. Caster wheels, used as support wheels, allowing free rotation. 3. Omni and mecanum wheels enable multi-directional movement. 4. Ball wheels provide 360-degree movement. Different wheel types impact how a robot maneuvers. Omni wheels, for example, allow robots to move sideways, whereas standard wheels require turning to change direction. Asterisk. Different steering models are used to control a robot's movement. Two-wheeled robots often use a differential drive system where each wheel is powered independently. Three-wheeled robots offer more stability, often using a caster wheel for support. Four-wheeled robots provide high stability and better traction. Some robots use motorized steering, while others rely on free-moving wheels. The choice depends on the application and terrain where the robot operates. Asterisk. Longitudinal control refers to how a robot regulates its forward and backward movement. It involves speed control, adjusting the robot's velocity. Acceleration and deceleration, ensuring smooth motion. Distance control, maintaining safe spacing between objects. For example, self-driving cars use longitudinal control to adjust speed automatically in response to traffic conditions. Asterisk. While longitudinal control manages speed, lateral control determines the robot's direction. It involves adjusting angular velocity, omega, controlling how quickly the robot turns. Steering control, managing left and right movements. Path following, ensuring the robot follows a planned route. For differential drive robots, turning is achieved by adjusting the relative speeds of the left and right wheels. Asterisk. To understand robot motion, we need to study kinematic and dynamic models. Kinematics focuses on position, orientation, and velocity. Dynamics considers forces acting on the robot, such as friction and inertia. Kinematics helps in motion planning, while dynamics ensures stability and energy efficiency. Both are important for designing a reliable robotic movement system. Asterisk. Differential drive robots use two independently controlled wheels to move. The robot's direction is determined by wheel radius R affects speed and torque. Wheel separation L determines turning ability. Wheel speeds NER and L. Adjusting speeds changes movement direction. For example, if both wheels move at the same speed, the robot moves straight. If one wheel moves faster, the robot turns. Asterisk. Now, let's take a closer look at a single wheel and how its motion is defined. A wheel has both angular velocity and linear velocity. These are two key parameters that describe how the wheel moves. The two quantities we use to describe this motion are velocity, ni, the speed at which the wheel moves forward; angular velocity, oi, the speed at which the wheel rotates. When a wheel rotates at a speed of 1 radian per second, it completes one full rotation every 6.28 radians, since one full circle equals 2p radians. Now, let's calculate the linear velocity for a specific case. Suppose the wheel has a radius of 0.1 m, and we want the linear velocity to be 3 m per s. The circumference of the wheel is 2pr equals 0.628 m. To achieve 3 m per s, the wheel must rotate at 3/0.628 4.8 revolutions per second. This means the angular velocity is 4.8 radians per s. By understanding these calculations, we can precisely control how fast a robot moves based on wheel rotation speed. Asterisk. Degrees of freedom define how a robot can move. Maximum of 6 DOF in rigid bodies. XYZ translation, forward, backward, up, and down motion. Pitch, yaw, and roll, rotation around different axes. Holonomic robots can move in all directions freely, whereas non-holonomic robots are constrained in movement. Asterisk. Let's examine an example in Weybits. The robot's wheel radius is 0.05 meters. The program runs in 32 ms cycles. Wheel circumference is 0.314 meters. The robot moves at 0.628 radians per s, meaning one full rotation takes 10 seconds. By using these parameters, we calculate the linear speed and stopping position of the robot. Asterisk. Well, now I went to calculate that speed correctly myself. So now I have the correct speed in that code down there. And now really then, if I really save that code in my own there, reset it and play it, then I really adjusted that heading value in such a way that it goes between that and then I changed the speed is correct. And now that it is turned in the right direction, you can see it driving forward continuously, updating the distance traveled. 1 square is half a meter, so it seems like the program is working correctly since it has driven that square, meaning we've gone about 50 centimeters. The goal was to drive 1 meter and 25 centimeters. So out of that opening, and just out of curiosity, the time is running, updating every 32 milliseconds. It looks like this operation is taking just under a minute. And then, just for fun, time is running, meaning it's updated every 32 milliseconds. And it seems that this operation takes just under a minute. So if you wanted to perform it faster, you would obviously need to increase the speed. We managed to get the robot out of this mini maze. Summary of Module 2, Locomotion. Locomotion refers to how robots move from one place to another. The most common methods include wheeled, legged, and tracked locomotion. Wheeled robots are the most widely used due to their efficiency and simplicity. There are different types of wheels used in mobile robots, including standard fixed wheels, caster wheels, omni wheels, and ball wheels. The choice of wheels affects the robot's movement capabilities. Various drive mechanisms determine how a robot moves. Differential drive relies on independent control of left and right wheels. Ackermann steering is used in vehicles with front wheel steering. Omni-wheel drive allows movement in any direction without changing orientation. The motion of robots is analyzed through kinematics and dynamics. Kinematics describes position, velocity, and orientation in relation to movement, while dynamics considers forces affecting motion. Mobile robots are controlled using two key principles: longitudinal control, which manages speed, and lateral control, which determines direction. By adjusting wheel speeds and turning rates, robots achieve smooth and efficient movement. Next, complete Quiz 1 and continue to Module 3. In this lecture, we covered the basics of robot locomotion, different wheel types and steering models, the importance of kinematics and dynamics, how differential drive robots operate, next steps. Complete Quiz 1. Move on to Module 3, Navigation and Motion Planning. See you in the next module.